Hi. Today we are talking about OP-based filters. Okay. So we are talking about how to use OP and RC to build active filters. So let's kind of review what's filters, right? So basically, if you have a R and C, right? So so if we're talking about filters, we're always talking about transfer function, right? So you have low pass, which provide a transfer function like this, and high pass, you provide a transfer function like this, and band pass, you provide a transfer function like this, right? So, and this is your edge of S, and this is your frequency, or edge of j omega, and this is S and this is the omega, right? So basically, if you wrote if this input and output, right? So V out over V in will be the impedance of the cap, right? So it's 1 over SC divided by whole impedance. This will be the SRC plus 1, right? So we usually so if this is H, right, equal to this one. So we usually can write H of S equal to 1 plus S divided by omega P whole. Okay. We call this then this one has a pole location, and it's at where. So that means 1 over S divided by omega P is 0. S is equal to minus omega P, right? So so kind of remind you some so what's the terminal? So the if the Laplace those terms, right? So basically, if S is a complex number, and so the poles can be anywhere on the complex domain, and so if you have h of S, then you can replace S with j omega to get the h of j omega notation, right? So it's 1 plus j omega divided by omega t. So so again, what if you you could have like say real pole. So if okay, right now we have a negative pole at here, right, at minus omega p, right, minus omega p. So you could have also a pole at a positive, so positive side, right? So that will be, for example, this is case A and this is case B. So case A will have something h of S. So case A, right, will be equal to 1 plus S of omega t, right? And for B, h of S the B will be 1 plus 1 minus S divided by omega p, right? So we kind of recall from the Laplace transfer function, right? If you have a S and if your real part of S is real part of S, so if it is S, if the real part of S is negative, then you have a damped response, right? So and you have some if you get some input pulse, then your response will be something damped, and this slope is defined by e to the minus z of t, right? So this so if the real part is negative. So if not, then you have a amplified result, right? So you get some response like this. So for the circuit to be stable, if real part has to be on the left side of the real part has to be negative. So this is unstable, right? So this is unstable, and this one is a stable one. Okay, and if what if the pole is at the j omega axis, so that's also unstable, right? It's oscillating. So it basically will maintain. If that one, if real part is 0, then you get constant. You get something like this, right? Basically the sinusoidal. Okay, and this is larger and larger sinusoidal. This is smaller and smaller sinusoidal. Okay, this kind of recapture what you have learned before, right? So this is the case where you have a pole at minus it's a negative single pole at minus omega p, right? So besides real poles, we could have complex conjugate poles, right? Something like this. And if it's a complex conjugate poles, so we then have a number of definition we can define for the complex conjugate poles. So usually complex conjugate poles, because they have two poles, it provides sharper filter than the single pole. Okay, so if you want to, so if you original, for example, if your single pole is a roll off something like this, so but if you have a complex conjugate pole, you probably will get something like more sharper. So if you want a sharper filtering, you probably have to resort to complex conjugate poles, right? Okay, so that's so much for the poles, right? So we also in some case we're interested in the high pass, right? So how do we use high pass? So basically, high pass is basically by swapping the position of the cap and the resistor. Okay, so this is C and this is R, right? So your transfer function right now, H of S will be R over 1 plus SC plus R, right? So it's a resistor divided ratio. So this will equal to SCR divided by 1 plus SC. Okay, so if also for this one, pole is a single pole, right? Single pole, and it's at where so if we wrote at where 1 plus SCR equal to 0, right? So S will equal to minus 1 over RC. Okay, so basically if we define omega p is 1 over RC, so that one will be RC SRC divided by 1 plus omega p, right? And this one will be okay. So again, this is the same as before, right? So it has pole at omega p. So but the difference is the denominator is not 1. It's a S of RC. If it's S RC, where so it has a 0, right? So 0 is where this guy reaches 0. So it's at where SRC will equal to 0. So S will be at 0. So you have a 0 at origin. If you have a 0 at origin, that means you'll be monotonically going up, okay, to infinite. If S is infinite, then your H of S will be infinite as well. So this is kind of interesting then. So you're starting to ramp up at 20 dB per decade. Then when you hit omega p, right? When you hit the pole frequency, then what will happen is your 0 wants to continue going high 20 dB per decade, but your pole wants going down 20 dB per decade. So what you get is actually flat. Okay, so you actually becoming flat because you're hitting another pole. All zeros, in fact, will cancel each other. Okay, so what you have is then a flat response like this, and then it's a kind of high pass at the very beginning. So and so when s when s is 0 or very small, so the transfer function is 0, right? And when s is infinite, then you have h of s equal to SCR divided by SCR, right? This guy gets cancelled. Sorry, S is infinite, so that will get 1. So this will be 1. Or like, so if you draw in 20 dB, but then if you draw in the body diagram, this will be 0 dB. So you have a something like this, right? So you have very negative until you come here. This is omega p. Then you become gain of 0 dB. Okay. So for the low pass, it's also something like this, right? 0 dB way down. Okay. Unless you have some gain afterwards. So otherwise your gain is 1, right? Starting from 0. Okay. So this is so far what we have is a combination of poles and zeros, and then you'll see the frequency behavior. So this is called first order. This is called first order section, right? Because it has only one. So it's only L and C. So it only has there is for first order systems. The only way you can only real poles, right? It's only single poles, not real. If it's single poles, it can only be real poles, right? If it's complex conjugate poles, it has to be 2. So then that's so much we have for first order. Okay, let's take a look at another second order system. So in this second order system, which will so it has like two active or two energy storing. So first order means has one energy storing device. If you have second order, so you have 2. Okay. So for example, if in the last example, this is R and this is C, right? What if you have a parasitic cap, CP? So R, V in and V out. Okay. So for this one, then we have a V out divided by V in will be basically this part, right? So 1 over SC divided by this part, right? So 1 over SC plus R parallel with SCP, right? So that's the parallel function, right? So if we reorganize a bit, so 1 over SC plus so something like this, right? So then we can cancel this 1 over SCP. So that will be so then if we multiply everything by SC times 1 plus RSCP, so that will be so then this function will be, right? So this function will then be, so your h of s will be 1 plus r s cp 1 plus r s cp plus c, right? Okay, assuming if cp is way less than c, so this can be approximated as 1 plus r s cp 1 plus r s c, right? So then you have omega z as the word, so it's 1 over RCP, right? And you have a P at 1 over C. So this will h of s will equal to 1 plus omega 1 plus s divided by omega z plus 1 divided by s divided by omega p. Right. So that's all you have, right? So you have a pole as 1 over RC, and you have a 0 as 1 over RCP. So you'll see the pole first, right? Then you see the Z, right? Because Z is much bigger. So if you see the frequency response, then you have omega Z here, and then you have omega P here, right? So and at 0, when S is small, so h of s is 1, right? Because this cancel. So h is 0 dB. So that's starting from here, 0 dB, right? So when you're starting to see the omega p, then it's starting to drop, right? 20 dB per decade, right? Okay, and so then you'll see after you hit the omega p, then you're starting to see the 0, right? The 0 want to go up, right? And omega p want to going down, so the net effect is flat, right? So instead of becoming so without the CP, it will be something like monotonic going down, right? So but here, after you hit the 0, it becomes flat, right? So at infinite, originally this should be very negative, right? So very, very small. So h of s, without this omega z, without this 0, this will be 1 over this one, right? So it will be 0, right? This is 0 dB and it's 1. Okay. So if it's like this, so that will be how much? Okay. If s is infinite, so then you get s of omega z divided by s of omega t, right? So basically it will be omega p divided by omega z. Okay. So that's the final value. Okay. So it goes to infinite. Okay. So this is another second order system. We saw a pole and then we saw a 0, and it's behaving something like this. Okay. So you'll say, oh, I really don't want something like this. I want instead of 20 dB, I want a 40 dB. We want a very sharp edge. Okay, how can we do it? So let's look at ways we can implement to realize that function. Okay, so let's look at a transfer function of h of s, which will be 1 plus s squared plus omega divided by omega. Omega 0 divided by q of s plus omega 0 squared, and this omega 0 squared. Okay. So if you have a transfer function of this, so very small, when s is 0, h of s say, okay, say something like S of 0, then your h of s will equal to magnitude of this one, will be, if s is 0, so it will be omega 0 divided by omega 0, so it's 1, right? 0 dB. Okay, when s is infinite, your h of s will be s squared of 1, so that will be 1 divided by infinite, 0, right? It's not 0 dB, it's like minus like 200, 300 dB, right? So, and also another one is s is equal to j omega naught. So h of s then will equal to, okay, if it's j omega naught, so that cancels this part, right? So that will be omega 0 of omega 0 q of omega 0. So that will be q, okay? So you will see something, okay, starting from 1 and then go finally to to 0, okay, to 0. And the natural frequency, we call it omega 0, natural frequency. So this is natural frequency. So then you reach omega p, q of, so you have a peaking somewhere, okay? So let's see, where is the pulse, right? So what we have is just we finding the frequencies, right? We still see when it's low frequency, when it's middle frequency, when it's high frequency, right? So, but we haven't taken a look at where is the pulse, right? So pulse is where where this one equals 0, right? So s will be 2 of minus omega 0 of q plus minus of something like this, right? Yeah. So if q is bigger than half, right? So omega 0 over q squared will be less than 4 omega 0, right? Right. If it's bigger than, if the denominator is bigger, then it becomes smaller, right? So this is then you have so this one is so this one has to be a complex number, right? So you have two complex poles. So if q is half, so you have a single pole which is at 2q of omega 0, right? So a single real pole. So if q is less than half, so you have s of something, right? We have 2 of plus q plus this number, right? So you have 2 real poles. Okay, so basically, okay, so if this is half 0.5, so if you have something, if you have a real pole, that means you'll probably have something like this. Okay, it's not that sharp at all, right? You're studying, it's very small. So then, if you have reached half, then again it's a single real pole, right? It's like your RC. It's just basically like what you had before, right? So like what you have in the first order before, right? So, and if it's bigger than half, then you have the it could be something like 10 or 20, etc., right? So depending on the cubes. So we have seen all this. We have known if it's real pole, single pole. So as you see, you probably want a complex conjugate pose because it provides sharper filtering, right? Now let's look at the location of the complex conjugate poles, right? So you have a pole here and then a conjugate pole here, right? So so the distance from here to the origin is called a d. So d is what? D is if you have s of a plus bj, right? So d will be square root of a squared plus b squared, right? So that will be square root of this will be 4 of omega 0 cubed, right? So this will be j, right? So plus this one, rho q minus 4 omega 0, right? Okay. So oh, sorry. Sorry, because this one is a negative number, so that will be has to be this way, right? So so that will be this minus this, okay? So that will be omega 0. Okay. So the distance between your pole and origin is omega naught, okay, your natural frequency, and the distance to the j omega axis, right? So that's your real part, and so this part is your real part, right? So that omega 0 over 2 cubed, right? So if the Q is large, right? If Q is large, so that will be small, right? So that means your pole will be very close to the origin, close to the j omega axis. So if your pole is here, okay, so basically if you draw a radius, right? If you have same natural frequency, but if now your pole 1 move here, pole 2 move here, so you know this one has the original, this one has a higher Q than this one, right? So basically that one will something like this, and this one will probably like this. This is for P1 and P1 prime, right? So that's show you the relation between your pole location and your transfer function. If Q is large, if Q of pole is large, right, or the second order section is large, then the omega 0 over 2q for the same natural frequency will be more closer to the j omega axis, right? So that's what I want to show here. So if I give you like a pole location, let's say I have two choices. One is this two, the other one is this two. For beta Q, you probably want to choose this two, right, instead of this one. So that's it. So we need to see how we can actually realize this function, right? So we know we have to build something like this for the second order one. So we have studied something called silent key. It's one implementation. So basically what we have is R. So it kind of trying to mimic a structure something like this, and R and a C. Okay, so it's called a ladder structure. Okay, so but there's no inductor in. That's not done easily. So what you do is to use a gain of 1 and some sort of positive feedback to mimic the inductor. Okay, it's R1, R2, C1, C2. Okay. So this gain of 1 can be done easily by op-amps, right? Plus, minus, so it's gain of 1. So this has the benefit of using just one op-amp. Okay, later we'll see something called Thomas, which uses 3 op-amps, right? So so this transfer function is some kind of omega 0 of s plus omega 0 of q of s plus omega 0 0, and omega 0 is 1 over square root of R1, R2, C1, C2, and q is something like C1 divided by C2 of square root of R1, R2, R1 plus R2. Okay. Okay. So when you are doing design, you probably are giving for filters, right? So you probably are given a omega naught and a q. Let's say I want a filter at 15 kilohertz. I want a q of let's say 0.1, something like that, right? So I forget to mention an important idea is so you have all kind of q's, right? Q of 10, Q of 5. So this is something called maximum flat one. For a maximum flat one, the Q is square root of 2, 1 over square root of 2. So that's called the maximum flat. You don't have any peaking. So that's also widely used. So if we have to choose Q of 1 over square root of 2, so what you can do? So let's say we're building a omega 0 of 10 kilohertz, right? Now what you can do? So you can pick a unique choice will be C1 is 2C and C2 is C, right? So this is 2 times this one. Oh, sorry. I saying wrong. This is C1 and this is C2. C1 and C2. So so this will be 2C and this will be C, and then so this will guarantee you a Q of 1 over square root of 2, right? So then what you do is you can choose R1 equal to R2 equal to R, right? So then your omega 0 will be 2R C, right? 2R C. Oh, sorry, square root of 2R C. then you can pick reasonably honestly value to meet your omega 0. Okay. So so this one has a good side is it's using only one op-amp. And and then it has large sensitivity to RC variation. Okay, so if RCs change, then that changes a lot. So for example, if Q, if it's something like this, right, you already have this one. So if R change like 10%, you may get something like this. Okay, so it's not that stable. So anyway, so that's a good for a first choice, right? Now, so we want to build a, so this is silent key low pass, right? So we want to build a high pass. So high pass, then we swap the position, right? So basically you'll have a R1, R2, sorry. So we swap this one. C1, C2, R1, okay? And so here is R1, and then you have some sort of gain built here. Okay, so basically this is to provide some gain and join by here. This is also there is another 2. Okay, so basically you most looks like what did you just swap, right? So then you have the same sort of omega Q equations. So turn out omega 0 is 1 over RC, and the Q definition you can read your text the lecture notes. Okay. So that turned out it will be just similar, and this one is just x squared. Okay. So you have 2, 0 at origin, and then you hit a complex conjugate pole at omega 0. Okay. So then that frequency response is you're going high, and then you hit the poles, right? So you have 0, and then you hit the poles. So if you have a complex one, then you have something like this. Or if you stamp the one, you have something like this. So that's for different Qs, right? So and finally you reach 1. So that's the high pass. Okay. So now let's talk about bandpass. So for bandpass, then you need something like this. So that will be a bandpass. Okay. So basically, you have a origin, you have 0 at origin. You going up 20 dB per decade, then you hit a complex conjugate pole, so you're dropping back 20 dB per decade. Okay. So so that's what you have. Okay. And there is implementation in silent key. So that will be something like this. You have an R, and you have a C, you have R, you have some. Right now you are going to use negative, something like this. sorry, no, you have something feedback. So this one is C, and this is R. Okay. So that implements this is the bandpass filter. Okay. Okay, so that's what I want to say about how do you build filters using using for one op-amps. Okay, so and we know it's called a silent key. So later, if people talk to you about silent key, you at least you know it's some sort of single op-amp structure, and it has benefit or the advantage of being simple. So you don't only need to buy one op-amp and building using some cheaper RCs. But the drawback is sensitive to the component spread, right? So if your RC value change, your pole and quality factor change a lot. Okay. So then we look at another topology. It's called Thomas. So Thomas. So this one has the benefit of being less sensitive to the component spread. Okay. But the drawback is it has to use 3 op-amps for a section. So that has a transfer function. Again, it's something like this: a squared plus mu0 dot over q s plus mu0, right? So that's as before. But right now you have a2 of s squared plus a1 of s plus a0. Okay. Now, so the implementation is something like so you have a OPE, and then you have a cap here. So using the negative feedback, inverting style, then you have this side, you have a feedback as well. And this is one of the output. And then you have another one. So, and then you hook up back to input. Okay. So it's like it's like a bunch of RC, RR, and C parallel with R section. Okay, and you have overall feedback. So so then you have minimum spread. Okay, so what you do is you have a unit cap C is always C here, and then so this one is R and this one is R, and this is R1, and then this one sorry, it's R3. And this is R2. This is Q times of R. Okay. So also, sorry, you have another R1 here. So this is your low pass output, and this is your high pass output. So this is your bandpass output, and so your low pass output is here. This is your low pass. Okay. Okay, so this one, last stage is basically this is basically what that is. This one is -1, right? So it's low pass, the minus low pass. Okay, just the band pass output. Okay. So 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 the low pass and the band pass output, right? So if you have EVP here, then your low pass will be simply so this is RC integrator, right? So so basically this one is minus SC divided by R of B, this node, right? B bandpass. So equal to -1 SCR B bandpass, right? This node. Okay. So 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 here will be so this node will be 1 over SCR B bandpass, right? So again, if you can think of here, then so basically if this is input, right? So we again we can use so basically what you have is you have a R1 and you have an R2, and then this is going to the negative terminal and plus terminal, and this one you have a C and you have an R, right? So R2, and this will go to your VVP. This is input. This one is SCR times VVP. Okay. So this is not R2, this is R, right? Okay, so oh sorry, this is R2, this is QR. Hold on, let me see. So this one is R. This one is QR. Okay. So basically you have a bunch of current, right? So this current, this current, this current, this current. Okay. So basically you can think of you can use this focusing on this current. this current will be say I1, I2, I3, I4, right? So I4 will be equal to I1 plus I2 minus I3, right? So I4 is what? I4 is SC of 0 minus V bandpass, right? And this one, I1 is what? I1 is V in divided by 1. I2 is what? This is R, and SCR 1 over VBP, right? Yep. So, and minus, this one is what? I3 is minus 0 minus VBP divided by 2. So then you get VBP will be R1 SCR1 of V in, right? Oh, negative, because it has a negative sign, minus SCR SCR of the LP, if we keep on using that one. So just let's say if we still using the minus VLP, right? So this is plus, and so minus SR2C of VBP. Okay. So and then VLP is minus SCR of VBP. Okay. So then you plug in there, then you get a transfer function of bandpass, which will be K of S omega 0 and S squared plus S of omega Q omega 0. Okay. So K is R over R1. Okay. And omega 0 is 1 over RC. And Q is R2 over R. Okay. So you get a bandpass equation, right? So if you have the bandpass, so you know your low pass will be basically bandpass times 1 over SCR, right? So that will be a bandpass of S multiplied by S of omega 0, right? So will be K times of omega naught S plus, okay? So that's whole thing. So it's low pass and band pass. And here I forget to mention bandwidth is 1 over R2C, okay? Okay, so that's what the whole thing we want to talk about. Hopefully you enjoy the lectures. That will conclude today's lecture. Okay, bye bye.